Welcome to the Foundry by Forge College. Now, if you tuned in for our previous explainer on the regulatory landscape, you know we spent a ton of time talking about the rules of the game, taxes, compliance checklists, and the absolute joy of government permits. But today we're transitioning from all that legal paperwork right into the physical and financial realities of mining. We are looking at the bleeding edge of hardware and operations. Because as it turns out, Bitcoin mining isn't just plugging a loud box into a wall and hoping for internet money while your neighbors complain about the noise. No, it is a highly optimized, beautifully complex engineering challenge.
Okay, so here's the engineering blueprint we're going to use to deconstruct a mining operation today. We'll start with the mining tech stack, then look at Layer 1, ASIC efficiency, followed by Layer 2, thermal envelopes. From there, we'll cover the site evaluation workflow and wrap it all up by modeling operational trade-offs.
Let's dive right into Section 1, the mining tech stack, and the three interacting layers of modern mining.
To truly grasp technological innovations in mining, you kind of have to think of a mining facility as a three-layer cake. First up, you have the hashing element, the actual silicon chips doing the heavy mathematical lifting. Second, there's the thermal and power envelope, basically how we keep those chips from melting down. And third, the operational layer, the fleet controls that keep the whole symphony playing together. Change one layer and it ripples right through the others. But before we get to the chips themselves, we absolutely need to nail down a crucial metric, one that's going to haunt every single financial model you ever build. Power Usage Effectiveness, or PUE. PUE essentially compares the total energy your site pulls from the grid to the energy that actually makes it into your computing equipment. Think of it like a tax. If your PUE is 1.2, it means for every 10 watts your miners use to actually hash, you're paying for an extra 2 watts just to keep the lights on, run those massive cooling fans, and stop the building from turning into an oven. Nailing down your PUE early on is absolutely vital, because that cooling overhead, it directly eats into your bottom line.
All right, moving down to the microscopic foundation of our economics. Layer 1, ASIC efficiency.
When we talk about ASIC efficiency, the ultimate canonical metric is watts per terahash, or W/TH. Honestly, just think of it exactly like miles per gallon in your car. A lower watts per terahash number means you've got a highly fuel-efficient vehicle. Dropping from, say, 80 watts per terahash down to 50 is a massive, massive upgrade. But of course, here's the catch. Just like buying a brand new top-of-the-line electric car, that high fuel efficiency usually means you're shelling out way more upfront, your capital expenditure or CapEx, just to save on the gas or electricity down the road.
Now, let's look at Layer 2, thermal envelopes, because we really need to keep this hardware from melting.
So, when you're running thousands of highly efficient chips at maximum capacity, they generate an astronomical amount of heat, like literally blistering. Historically, the solution was pretty brute force. Just blow a ton of air over them in a giant warehouse that sounded quite literally like a jet engine testing facility. These air-cooled setups required giant overhead fans, perfect ambient airflow, and they usually run a PUE somewhere between 1.10 and 1.30. On the complete opposite end of the spectrum, we have immersion cooling, and this is exactly what it sounds like. You are literally submerging your incredibly expensive heavy computers into a high-tech bathtub filled with a specialized, non-conductive dielectric fluid. I know, it sounds totally crazy, but it works brilliantly. It's virtually silent, lets you pack machines way tighter together, and drops your PUE down to an incredibly efficient 1.03 to 1.08.
But hey, hold your horses before you go out buying giant fluid bathtubs for your rigs. Here's a quick callback to our regulatory landscape explainer. Remember how we said everything is connected? Well, cool new tech like Immersion isn't just a fun engineering upgrade, it is a massive regulatory hurdle. Giant tanks of fluid are incredibly heavy. That means you need upgraded structural support for your facility. And you better believe local governments are going to demand some extremely strict spill containment permits before they let you pour a single drop of that fluid.
And speaking of thermodynamics, there's another amazing innovation sitting in this layer, energy recovery, or heat reuse. Instead of just blowing hot air up into the clouds, miners are literally heating greenhouses. Yes, you heard that right. You can grow tomatoes with the exhaust of Bitcoin mining. Miners are taking the low-grade heat generated by their ASICs and using it to warm up local agriculture, heat office buildings, or even provide process heat for local manufacturing. It's a fantastic way to create a secondary revenue stream that offsets your net electricity expenses. The really tricky part here, though, is what we call heat grade matching. You have to pair the exact specific temperature of your exhaust with an industry that actually needs exactly that temperature. So it definitely requires some serious heavy-duty integration work.
So if we pull back and map all this out, the overarching theme here is trade-offs. Look at a legacy ASIC. It's super cheap to buy, incredibly simple to plug in, but the efficiency is just terrible. On the flip side, a brand new, high-efficiency ASIC completely submerged in immersion cooling gives you incredible, jaw-dropping efficiency, but your CapEx and your deployment complexity just go absolutely through the roof. It's the classic engineering rule, right? There are absolutely no free lunches. Every single efficiency gain you make comes with higher upfront costs or deployment friction.
Which brings us perfectly to our next section. Number 4, site evaluation workflow. Let's take this from theory to practical execution.
Mapping out this workflow in the real world is kind of like a 5-step instruction manual. Step 1, you've got to collect your baseline. What are your grid limits? What are the local regulations? Step 2, you create a short list of the technologies that actually fit within those exact constraints. Step 3, you quantify your expected PUE and your duty cycle. Basically, you're calculating how often your machines are actually going to be running. Step 4, you translate all of that data into a hard financial assessment line item. And finally, step 5, you write out your sensitivity notes, which are essentially stress tests for your entire business plan.
And that leads us to step 5, modeling operational trade-offs and running the actual numbers.
Let's run a quick Python model on 2 different setups. By the way, this is something we actually do a lot in our structured learning programs over at Forge College. So, let's look at configuration A. This uses a recent, but maybe not absolute top-of-the-line ASIC with traditional air cooling. It's giving us 70 watts per terahash, costs about $2,000 up front per machine, and has a PUE of around 1.15. Then, we look at configuration B, the absolute bleeding edge. We're talking high-efficiency ASICs submerged in liquid immersion. It boasts a beautiful 50 watts per terahash and a tiny 1.06 PUE. But it comes with a hefty $3,000 CapEx price tag per machine.
Now, when you model this out for an entire year across a whole fleet, the difference in annual electric cost is just staggering. Configuration A's traditional setup burns through significantly more cash over time. Meanwhile, Configuration B's lower watts per terahash and hyper-efficient PUE massively reduce that ongoing electricity burn. You definitely paid more upfront, but your daily survival cost, much lower.
But wait, remember step 5 of our workflow? We have to stress test this model. Because let's be real, the real world doesn't care about your perfect spreadsheet. What happens to configuration B if the local electricity price suddenly jumps 20%? Well, its superior efficiency actually protects you way better than configuration A would. But what if ordering those fancy immersion ASICs causes a 90-day shipping delay? Or what if the city halts your construction for 3 whole months just to review your spill containment permits? Choosing your hardware is intimately, unavoidably tied to real-world delays and regulatory coordination. The absolute best tech in the world is completely useless if it's just sitting in customs while your competitor is already hashing away.
I want to leave you with a bit of a provocative thought to chew on here. As the network grows and global power grids get tighter, will future physical and regulatory constraints make extreme technologies like immersion cooling and heat reuse absolutely mandatory just to survive? Or are they going to remain a premium luxury reserved for only the most well-funded operations? It's the multi-million-dollar question every major miner is grappling with right now. If you found this stuff fascinating and you want to dive deeper into these models, build out your own operational spreadsheets, and continue your Web3 learning journey, I highly encourage you to check out forge.college. There's a whole world of data just waiting for you to explore. Thanks so much for joining me on this explainer, and I'll catch you in the next one.